All right. Let's give everyone a few moments to kind of log in. We're a couple minutes late today. Exchanged machines at work today, and I forgot to preset my key in the OBS display driver on my new machine, so I had to go and rekey it. All right. We're a little bit early today. We might people catch them off guard, so let's get this show on the road. Greetings, tech artists from around the world. It's Friday, and it's noon, a little bit early. And it is Friday, and it's noon, so that must mean, that must mean it's time for another episode of Tech Art Talk. Live, that's right. Hey, my name is Chris, and I am going to be your host for today. Now, we're on a big old subtopic. We're dealing with Hlsl, and we're dealing about shader writing. So we're basically going through all about materials. All right, last week we started going on into the Phong component of rendering. Remember, there are three components that we have to deal with. We have to deal with, when doing any kind of lighting, we got to deal with ambient, we got to deal with diffuse, and we got to deal with Phong. And now last week we started off with ambient and diffuse. This week we're just going to focus on Phong, and which is kind of like a little topic unto itself. So that's why we're going to spend a whole episode just on Phong today. And we're going to continue off where we left off last week. You know, we're going to build right upon the shader of this. Now, if you didn't happen to tune in last week and you don't have a version of that shader, that is okay. I'm going to do a quick little review and go over all of the work that we did last week in order to prep for today's lecture. So with that said, let's get things rolling. All right. All right, let me make sure that this is cool. Yes, that is what I want. And I'm going to resume that. Okay. And, oh, we got to change it over. We're still onto this. And so let's go into take off where we left last week. Here we go. Last week. Here we go. Now this is where we left off last week, where we have just our ambient and our diffuse lighting. Now notice here, I rotate my camera around. You see the back side of the object. The back side of the object is dark, and this is the ambient light. So this is what the color of the object looks like inside a shadow. Now here we are, we're going to rotate the camera around to the front side of the object. Now you see we have a bright section over here, and then it gradually gets dark as we go on to the side. That is the dot product of the normal and the light vector, and that produces that gradient. Now remember, in order to do this, during the last part of the lecture last week, we created something called a common Hlsl, and the common Hlsl is just kind of like an extra file that we created along with our shader in order to create to kind of clean things up a little bit. Now it looked like this. Now we have this little global define called flip texture Y. We set that to 0 because for shader ed we don't need to do that. But on other environments you might need to do that, and so that's why we're including it. And so we're going to include 3 global matrices in order to process everything, and we know we're going to deal with it every time. We're going to need the world matrix, which is all of the rotations and translations we perform on our geometry. We have our view matrix, which is the matrix which transforms our object from world space into camera space, and then we have our projection space, our projection vector matrix, which translates our object from camera space into projection space, and that gives it a nice perspective angle. We also have our utility function. This will do the coordinate flipping if we so need to, but in this case we don't need to do that, but we're including it just as a frame of reference again. All right, let's take a look at the shaders that we developed for our Phong lighting model last time. I'm going to edit all the code. Okay, so let's take a look at the vertex shader. Now we have a vertex buffer per frame, and this is a C buffer type, and this is going to constitute the light direction. Remember, the light direction tells us where the light's coming from, and if we modify the light direction, if we move this back and forth, we can see that the light now moves there and then moves it up and down. Okay, so the light direction, imagine we're using an infinite light source. We're using a directional light, and so the only thing that really matters is where is this light pointing. We don't really care about the light's position any, which is actually kind of nice. That means one less thing to worry about. Okay, let's look at the input structure going into our vertex shader. We have the object position, we have the normal, and we have the texture coordinates. Okay, nothing too difficult with that, but coming out of the vertex shader, we have the position, the texture coordinate, the normal, and we also have the light direction. Yes, we do have to process the light direction in the vertex shader. Now if we look in the actual vertex shader code, we first take our object and then we put it into world view projection space. So we got our object, which is put our in position for every vertex. We multiply it by the world, then the view matrix, then the projection matrix, and then we're going to take our texture coordinates and then we're going to modify our texture coordinates and we're going to make some modifications to it however we need. Then we're going to take our normal and then we are going to normalize our normal. Normalizing, what does that mean? Is that we're going to give it a length of 1 so that all we're dealing with is actually the direction of our normal, and this is, remember, this is the little arrow that shows where the point is perpendicular to the curve of the surface. And then we do the same thing to our light direction. Our light direction is going to take the angle or the vector from the light pointing onto our surface. We're going to switch it around and then we're going to normalize it, give it a value, a length of 1, and then we're going to output this to our light direction. Now let's take a look at a Phong shader, the pixel shader. Okay, we have a C buffer up there, and we'll call this the C buffer per frame, and that means we're going to input the ambient color, which is the color of what the object looks like in shadow. We're going to input the light color. This is the color of our light, and the input data structure for our pixel shader is exactly the same as the data structure coming out of the Vertex Shader. It's the exact same. We're also going to deal with a texture 2D object. We're going to call it texture map. We're going to deal with the color sampler, which is a sampler state, and we're just going to keep it simple. We're just going to use linear filtering for the minification, the magnification, and the mipping. And for the address U and the address V, we're just going to keep that as wrap. Now, in our pixel shader, what we're going to do is we're going to normalize our normal again, and we're going to normalize our light vector. Why do we do that again? Is because when it goes through the rasterization process, weird things might happen. And suddenly when it's getting kicked out of the rasterization and into the pixel shader, that normal and that light direction may no longer have a magnitude of 1. It might be something different. And so we're just going to guarantee that it's going to be a length of 1, and then we're going to normalize it. Then we're going to take the dot product of those two. What's the dot product do again? That ultimately calculates the angle between the two vectors. So we've got the vector angle now. It's stored in n.l. Then we're going to get our color from our texture map, and then from that we're going to get our ambient value. And now let's compute the diffuse value by say, okay, if n.l is greater than 0, then we're going to compute the diffuse color by multiplying our n.l basically by our light color alpha, and by the color of the texture map. Then we're going to combine these two together. We got the ambient plus diffuse, and now that we have the color. Okay, so now we are ready to actually start creating our Phong shading to calculate the specularity. It's a little bit more involved, so hang on tight. So the first thing we're going to do is we're going to go bop into our Vertex Shader, and then we are going to add a new element to our V buffer per frame. And so what we have to take under consideration now is not only the light direction, but we have to take under consideration where the camera is from. All right, we've got the camera position in there, and that's coming in as a float 3. And for as an intrinsic, we're going to identify it as having camera position. Now notice that when we go ahead and save this, the camera position didn't top up into our pinned variables. Why didn't it? Is because it's understood as, since we put down camera position, it means, okay, where the camera is now. And so right now our camera value, our camera position is changing as we're floating around there. So that gets put in automatically, and it's because we put that intrinsic value in there. All right, now we're going to have to add some extra stuff to the pixel shader. Now look at here. This is a C buffer per frame, so that means this is the value of our context buffer on a per frame basis. Now, when we're dealing with the specularity, we're going to have to deal not only on a per frame basis, but we're going to have to deal with a per object basis. And so therefore, I'm going to create a new C buffer, and I'm going to call it P buffer per object. And I'll call it P, meaning for Phong shading. And inside of that, we're going to want the specular color, which is the specular color of our light, and the specular power. Remember, the specular power is the value which is going to control how big or how small we want our specular hotspot to be. The larger the specular value, the more tight, the more precise our specular hotspot is going to be. And the smaller it gets, the larger, the more diffuse it's going to be. Let's go ahead and save it. And notice that once we save those, the specular power and the specular color were now promoted down to our pinned variables. So let's give our specular component an obnoxious color that is going to show up so we know that it's working when we want it going. So let's go for a nice, let's go for magenta. Yeah, a nice obnoxious magenta. Yes. And so for specular power, let's give it something kind of like in the middle, maybe like 25, something like that. Usually 25 is kind of like in the middle. 10 is going to be, produce a much larger, more diffuse specular component. 50 is going to produce something that's really hot usually. So let's put it someplace in between. Okay, we've got that in place now. So let's go ahead and start making modifications to our data structures. The data structure is going, data structure, we had to modify our data? Yes, we do. Because remember, we're no longer dealing just with our the position of our object and our light direction. We now have to take under consideration our view direction. So now what we're going to have to do is create our view direction. So where is the light actually coming from and where is it pointing? So therefore, we're going to add that to our data structure as a float 3. And as a semantic, we're doing a text chord 2. Now, you'll see that in Hlsl, you can add semantics just about anywhere you want. And you could put text chord 2 in there, text chord 1. You could add as many text chords as you want to. And it's just kind of a good placeholder to say, like, okay, we know that it's there, but I don't have anything kind of fancy for it. All right, now, once we made this change to the Vertex Shader output, oh, look at that. I did it in the pixel shader instead. Dopey me. Well, okay, I did it into the input, so I kind of got ahead of myself. So we've got the view direction, so let's go ahead and make this change to our Vertex Shader output. And I'm just going to put the exact same variable. So our data structure coming out of our Vertex Shader should be exactly the same as our data structure going into our pixel shader. All right, with that said, let's make our modifications to the Vertex Shader. Remember, when we were doing the Vertex Shader, we got our light direction and then we normalized it. Well, we're going to have to do the same thing to the view direction. But in order to get the view direction, we're going to have to get the point on the surface. Now, the point on the surface, we want to be in world space. Now, we have our point position on here. And by the time we multiply it by the world matrix, the view matrix, and the projection matrix, it's no good for us. We're not going to like it. We just need it to be in world position. So what we're going to do is we are going to multiply our object position by the world matrix. And that's going to get our object, or our point on the surface, in the right proper space. Okay, so we now have our object. We're going to call it world position. It was an in.object position multiplied by the world matrix, and we only want the x, y, z of the result of that multiplication. Now what we're going to do is we're going to subtract the world position from the camera position. And so what that's going to do is going to produce a vector pointing from the point on the surface towards our camera. And that is going to we're going to normalize that, and that's going to give us our view direction. So once again, we're going to get our view direction by we're going to take our camera position, we're going to subtract our world position from it, and then we're going to normalize it. Okay, so not many modifications need to be made to our Vertex Shader. So let's go ahead and make the modifications to our pixel shader. Now, the pixel shader is going to require a little bit of configuring. Now, we have our pixel shader. Now, we have our pixel shader, which is like in the process of being made. So what we did here is we got our light direction, and then we normalized it. So let's go ahead and do the same thing for our view direction. And I'm going to just make myself a little bit of space here. And then we're going to take our view direction coming from our Vertex Shader, and then we are going to normalize it, or convert it to 1, a length of 1. We're going to get a specular value. We're going to float 3, and we're going to initialize it to 0. So this is going to store just our specular component. So here it is, one little statement to calculate our diffuse. We're going to need a lot more when we're going to calculate our specular component. All right, there it is, gang. So the first thing what we're going to do is that we are going to calculate our reflection vector. Now, our reflection vector was that horrible formula that I gave you earlier, and it is the 2 times the n dot L times n minus L. Okay, that's what it translates to. Here it is, 2 times n dot L times the normal, subtract the light direction from it. All right, and then we're going to normalize it for good sake. Because remember, when working in shaders, we like to normalize our vectors to make it look light. Okay, good. Okay, and now in order to calculate our specular component, what we're going to do first is we're going to take the dot product of our reflection vector against our view direction, which is pointed towards our camera. That's going to give the angle between the reflection vector and our camera. And we're going to take that angle, and then we're going to saturate it. You're probably going, hey man, you've never used saturation before here. Okay, saturation is just going to force or kind of clamp the result of the dot product to be somewhere between 0 and 1. But you're going, well, isn't that just cosine? Yes, it is, but it's just kind of a more thorough way of shader programming in case something nutty happens, and in case any kind of weird abstract values come through, we're going to make sure that it is within the proper range of 0 to 1. And so that's what the saturate does. Okay, so then we're going to do that, and then we're going to take the result of that, and then we are going to drive it to the specular power. So what we're going to do is going to take the power of our the specular highlight, and we're going to take it up to the specular power. We're going to raise it to the specular power. That's right. And then here's another bit of cleanup that we're going to do. We're going to give it the minimum value between our specular power and the alpha of our color of our texture map. So what that's going to do is guarantee it's going to be no greater than 1. And so if our object is transparent, then that transparency is going to be stored within that W value. And the transparency means it's no longer 1, meaning it's opaque. Now if it's like 0.5, that means it's half transparent or half opaque. And so therefore we want the color of our specular color to be knocked in half as well. So that's what this does, is it takes the minimum of the specular power and the minimum of the color of W, and it takes the smaller of the two. And so therefore the specular then component is then our specular color.rgb times the specular color times the of the alpha times our spec min, and this is going to give us our specular component. And so the last thing to do is just, here is our out.rgb equals our ambient plus our diffuse. So let's just add our specular value. Okay, there it is. Ambient plus diffuse plus specular. And, oh, we don't have any specular. Why is that? Well, gang, guess what I forgot to do? Here we have our specular color. Don't forget, we're multiplying by the specular alpha. And you're going, wait a second, multiplying by the specular alpha? Yeah, that's once again just one of those little things to do. And look at where the specular alpha is here. It's located at 0. We got nothing, nine, nunca, nada, het roy. And so let's put it up, give it a value of 1. Yep, and there it is. There's our nice green, there's a nice magenta specular highlight. How do we know it's our specular highlight? Let's go ahead and change our view direction, or light direction around. We move it around between the right and the left. We can see the specular hotspot move around, and we can move it up and down. Okay, so we can see that the hotspot does work. And then when we move our camera around, we'll see that it kind of sticks around and goes over to that direction. And you'll see that it kind of, the hotspot kind of like widens out and gets kind of flat the more perpendicular we go for it. All right, so what about the specular color? Remember, if we increase the specular power, we're going to sharpen or make the specular component a little bit smaller, but it's going to be brighter. So if we push that up to something like around 50 or 60, it's going to be small and very bright. Now if we bring that down to something like 10, it's going to get more diffuse, more spread out, but it's not going to be as bright in that hotspot anymore. So I'm going to put that back to about 25 to be right about average here. And there you go. There is the full-blown Phong specular lighting, implemented in its full pride and glory. All right. Now, remember, BlinnPhong was a graduate student over in the University of Utah, and those guys were pretty sharp over in Utah back in the 70s, and they really knew what they were doing when they were inventing computer graphics. Well, there was another student along that was hanging out there, another guy, another student, you might have heard of him, a guy named Jim Blinn, you know, another one of those little guys that was kind of like hanging out and just kind of like, not really doing too much of the whole graphics community. Yeah, right. Yeah, okay. Blinn came along and said, okay, BlinnPhong came up with this awesome model. So if he has this awesome model, it's cool, but it's a little bit slow. So what Blinn did was said, okay, I'm going to come around and let's go ahead and speed it up a little bit. So what I'm going to do is I'm going to take a copy of my Phong pixel shader. I'm going to copy it right over to here, and I'm going to call it my BlinnPhong. Because ultimately it's still the Phong shader, but we've got the blend optimization on here. And what is the blend optimization? Okay, the optimization is that Jim Blinn found out that you could take something called the half angle between the normal and the reflection angle. And then if you put that half angle into the operation instead of the appropriate view angle, it would work just the same. And what that does is it removes one or two calculations and it works just fine. So what we have here is the BlinnPhong. And so what was the modification we're going to do for our blend? Okay, so first what we're going to do is we're going to calculate our half vector. And the half vector is actually kind of easy to calculate. And so we're going to get rid of this reflection vector stuff. And so here's our half vector. And all we're going to do is we're going to get our light direction and then the end view direction. Okay, so what we're just going to do is normalize that. And that's the process. That's all it is you're just going to get the light direction added with the end view direction, and we're going to normalize it, and there's our half vector. You know, piece of cake. So all we have to do is now we're just going to take the dot product now of our normal and our half vector. And oops, looks like got a typo error there on line 99. Let me go ahead and let's see if we do this, change this. Oh, I forgot to put a comma on there. All right, there we go. Oh yeah, let's go ahead and change this to our appropriate shader. So we have the properties of our, so let's change this from the Phong pixel shader to our BlinnPhong. So BlinnPhong pixel shader. Okay, there it is. Did you see it, folks? Did you see the change happen? Well, you didn't see it happen, did you? Well, it's because it's basically doing the exact same thing. We just reduced the amount of calculations to it. So Jim Blinn figured out a way of making this operation a wee bit faster and a wee bit more optimized. Okay, and that's really all that BlinnPhong shading is. And so it's not really that much of a difference there. Okay, but if you look at this pixel shader is starting to get a little bit obnoxious. It's starting to get a little bit large. It's starting to get a little bit mean. So let's go ahead and simplify it. And so ultimately we're still going to do the BlinnPhong operation, but now we're going to combine it to do some intrinsic calculations. And so when they created Hlsl, they said, okay, well, let's take all these operations because we're going to be doing a lot. We're going to be doing a lot of shading. Let's go ahead and make an intrinsic operation to kind of do all this stuff for us. And so in order to do that, first we're going to need to create ourselves some kind of helper functions. And so these new helper functions are going to grab color information from the ambient, and the diffuse, and the specular components. And let me go ahead and add this. Okay, so the first vector is just going to return a float 3, and it says get vector color contribution. So the input is the light, which is a float 4, and then here's the color. And so all we're going to do is multiply the light times the intensity of the alpha, the light intensity, and we're going to multiply it by the color. And so that's what's going to give us our overall color. Not terribly difficult. And so we're going to do a get scalar color for color choose. We're going to use this for the specular component. And then all we're going to do is going to take the color RGB, we're going to multiply it by the color of the intensity, and then we're just going to get our float color here. Now here, our float color is going to be a float, and it's not coming in as a 3 value. That's because the value coming out of our specular component is a float rather than a vector. And so we have to get these two functions in here now. All right, so we've got that. So we've got those, and then we've got our, let's go ahead and create a duplicate of our BlinnPhong shader. And I'm going to call it BlinnPhongIntrinsics. BP starting for BlinnPhong. BlinnPhongIntrinsics. Pixel shader. Okay, we've got that going now. So let's go ahead and change this over to BlinnPhongIntrinsics. BlinnPhongIntrinsics. Okay, so we know it's now working. So let's make our modifications. Now, I don't want to go ahead and type this in because it would take me too long to type in. But let's go ahead and set things up as we would normally. Okay, so in this first part of the shader, all we're going to do is just grab our basics. We're going to get our normal, and we're just going to normalize it. We're going to get our light direction coming in from the vertex shader. We're just going to normalize it. Same thing with our view direction. And then we're going to take our light direction, and we're going to dot it against our normal, and that's going to produce n.l. We're going to get our half vector, which is our light direction, added with our view direction, and then we're going to dot it against the normal as well. So we've got a lot of dot products against the normal. All right, and so what we're going to do next is then we're going to calculate using the intrinsic function put inside of our Hlsl library for us. And there it is. So what we're going to do is we're going to say, okay, we're going to get our initial color from our texture map. And then here's the magical sauce, gang. Light coefficients. Oh, this shouldn't be my lit. This should just be lit. And then the input for that is the n.l, the n.h, and then the specular power. So that's what's all going into it. And then this is going to calculate our lighting. And so therefore, we're going to get our, okay, the result of our lit, it says returns a light vector for the ambient, diffuse, the specular, and 1. Ambient is always 1. The diffuse is going to be whatever the diffuse vector is going to be. The specular is going to be the specular component, and 1 is 1. So that it always returns. Now, I don't know why they made it a float 4 when they're only going to be returning back 2 values, diffuse and specular, but that's what they did anyway. Okay, so there is all of our lighting calculation put into one little function called lit for us. So isn't that nice? They put it all into the light coefficients. So we're going to grab our vector calc contributions to create our ambient color. And then we're going to do the same thing to our diffuse, which is our light color. And notice here we're going to grab the Y component from our light coefficients. And so that is going to be multiplied against the color of our diffuse light. And then the specular, we're going to use the get scalar color contribution function. And this is going to be our specular color, and we're going to have the minimal value of the light coefficient of our Z, which is the Z value of our light coefficients, or versus the alpha color of our light, which is, usually 1, but it's going to take the minimal of the 2 values. And so we're going to get our ambient, our diffuse, and our specular colors, and then we're just going to add them together. And we're going to take a look at it. And everything disappeared. Okay, gang, it is disappeared, and this is not fun. All right, so something happened around here, but what ultimately has happened is the lit function implemented on ShaderEd doesn't work. Yeah, I know, I hate to pass the buck onto somebody else. And did I spell this right? BlinnPhongIntrinsics pixel shader. Let me just make sure that this is right. So we should get something a little bit here. Oh, there it is. And you'll notice that it's broken. It's broken, so look at that. Okay, I did some research into this, and I looked up the value, and it turns out that the specular value coming out of this is also returning a value of 1. It's constant value of 1. So the specularity is always going to be 1. So that means the ambient is correct, the diffuse is correct, but the specular value, it's clamped at 1. Now, this is a bit of a conundrum for us. I'm going, man, I'm doing a broadcast here, and I'm going to be showing off how to use the lit intrinsic function in Hlsl, but it doesn't work. Okay, so what I did was I went over to the Microsoft website. I checked out, I said, okay, I did a research and I looked for it, and I said, okay, fine it is. And so what I did was I figured out, okay, let's make this a nice simple little function that kind of replaces it. I'm going to call it mylit. And so it's really not that complicated. So mylit, it doesn't really do a whole lot compared to it. Here's our input. We have our n.l, our n.h, and our specular power. And so here we go. We're going to say if n.l is less than 0, then we're only going to output kind of the black value. We're going to put that into the green. Otherwise, it's going to be n.l, and that's going to be our diffuse value. Here we go. If the n.l is less than 0, or if the n.h is also less than 0, then we're just going to return black for the specular component. Otherwise, we're going to take our n.h and we're going to raise it to the specular power and put that into the blue component, which is going into our specular component. And that's really all that there is, folks. And so let's go ahead and change our function over to use mylit function rather than the intrinsic function. Mylit, and there it is, back to normal again. And now it's behaved exactly as we expect it to. All right, now we know that it's working, so let's go ahead. We can change our specular color around. We can change it from a magenta. We can make it kind of green looking. We can take our light. We can move it around just to prove that it is functioning properly. And there you go. Okay, gang. That's what we wanted to discuss today. And so what we did was we went over 3 functions to calculate the specular component of our lighting. We did the initial Phong lighting, which is the kind of the earliest and the one that kind of set the standard for everything. We did the BlinnPhong variation, which is an optimization, and it kind of makes the operation go a little bit faster and a little bit snappier, but produces the same results. And then we have the BlinnPhongIntrinsics, which kind of helps make our shader writing a little simpler and makes things a little bit more organized. All right, folks, great. Thank you very much for joining me today. Let me see if I'm going to go ahead and resume my slideshow. Oh, great. It didn't do that. So what I'm going to do is I'm going to go and shift over to moi. And look at that. I can't believe my camera's frozen. Ah, come on. Okay. Now I unfroze it. Okay. That means my picture was frozen the whole day. That'll teach me to change machines. Everything's going to screw up again. All right. So in the meantime, what I'm going to do here is I'm going to fast forward through my presentation and get all the way into my resolution here. So ashamed. Catastrophe of errors. Hey, but life is always exciting when dealing with TechArt Talk. You're never really going to know what you're going to get. That's why you got to tune in. I have a hunch for what we're going to do here in a couple weeks. We're going to go from a live broadcast to a nice, clean, pre-recorded content, and we're going to get rid of all this garbage and all of this chaos and all this regular hanky-panky that kind of makes TechArt Talk so live, so interesting. All right.